Hello, CBSE 10th graders. Welcome back. This is Pooja, and I hope you all are doing good. In this video, I'll be discussing about the sample paper for the term 2 for CBSE class 10th. Okay, and the topic for discussion here will be magnetic effects of electric current. So there are a couple of questions which are included in the sample paper of this topic. So let's quickly discuss. Before we go ahead, let's discuss about the general instructions. So these are the basic instructions which you have to follow during the exam. All the questions are compulsory. There'll be 3 sections, section A, B, and C, and there will be respective questions in each section. Then we'll have the internal choice. Okay, so in this question, if you will have internal choice, don't try to attempt both the choices. Okay, sometimes the student is trying to fool the examiner and he's trying to attempt both the parts. Okay, so examiner might get frustrated and you might reduce your marks. So don't try to do that and try to attempt only one part which you know the best. Okay, so let's go ahead. In the section A, there was a question number 6, which was as follows. And in this question, as it is shown here, we have horseshoe magnets, the North Pole and the South Pole. We have a rectangular bar as a rectangular coil we can see here, and this is a battery, right? So what will happen, what they are asking in this question is that for this position, state the direction of the force on the arm AB. So this is the position, and they are asking us what will be the force which will be acting in this arm AB, whether the force will be in upward direction or it will be in the downward direction. So that is the answer we have to give. Okay, so now as you can see, the magnetic field lines always move from north to south, right? So magnetic field lines will be propagating like this, right? You are clear with that thing? The current through this arm is moving from A to B, right? Why it is moving from A to B? Because this is the positive terminal and this is the negative terminal of the battery. So the current will be propagating like this. Okay, so the current is propagating like this, and finally what will happen, what we have to determine, what law we have to use, what rule we have to use. Yeah, I know you all are familiar with that. That is Fleming's left hand rule. So that is Fleming's left hand rule. So according to this rule, just remember 2 simple points for this rule. You always have to use your left hand for that, and always start from the thumb. Okay, start from the thumb, remember. And just 2 points which you can remember for this is that first is that always start from thumb. So start from thumb. And the second is that remember a word F, B, and I. What does that mean? F is the force, B is the magnetic field, and I is the current. Okay, so if you'll remember this thing, you will be easily able to find out the direction of the force. So Fleming's left hand rule, which is used to find out the direction of the force, what will happen? Now place your fingers accordingly. Okay, so this is F, B, and I. B is the magnetic field which is propagating from north to south. I is the current. Okay, the current is propagating in upward, like in this direction, right? Then automatically you will see your thumb will come in the downward direction, right? So according to this rule, what we can say that the current, the force which will be acting on this arm AB will be in the downward direction. Similarly, because here the current is reversed, you will find that the force will be acting here in the upward direction, although you don't have to find out that thing, right? So what will be answer of A part? For this position, state the direction of force on the arm AB, that is in the downward direction. Why does the current in the arm BC not contribute to the turning force on the coil? Obviously, there's a current which is flowing through this BC and this DA part also. So why that is not contributing? You know, so the question they are asking us, we have understood that thing. Now, why that is not contributing? As you can clearly see in this picture, students, that the current is propagating from B to C, and the magnetic fields are also in the same direction. When the magnetic field lines and the current, they are in the same direction, then the force will be minimum, or we can also say this force will be 0. Why? There is a rule, there's a formula which you'll learn in your higher class, just to memorize, just to have a visual picture of that thing, to understand that thing. Let me just tell you quickly here. So force is given as QVB sine theta. Okay, when you will solve this thing, you know that velocity is distance by time. So simply you have put the values and finally this is the formula which has been appeared here. So F is equals to BIL sine theta. This theta is the angle. This theta is the angle between the B, the magnetic field, and the current. Right? So if the angle between I and the magnetic field, as in our case, we saw that the magnetic field, this is from north to south in the same direction, and in the same direction we have the current, right? So if magnetic field, that is B and I, they both in the same direction, what will happen? Theta will be 0, right? So if theta is 0, sine theta will be 0. Or in other words, I can see the force acting will also be 0. Right? So this is the way you can write in your exam. The first part is clear. Second part, because BC is in the same direction as the direction of the field lines, the force is minimum or it is 0, right? When the direction of the current in the conductor is same as that of the magnetic field. When the current and the magnetic field, they are in the same direction, the force is minimum, or we can rather say it's 0. So BC will not contribute, as the force on it, this part will cancel by the force on the DA part. Okay, now here we have a OR part. So either attempt the above question or this one. Okay, so we have a circuit which contains a battery. You can see here we have a battery here. There's a variable resistor here, and finally this is a solenoid given here. And what question they are asking us? Let's see the A part. State how the magnetic field pattern indicates regions where the magnetic field is stronger. So now they are asking us where the magnetic field is stronger. Okay, so the magnetic field lines will be stronger. We have studied that where they are more close to each other. More close to each other, that means there the magnetic field strength will be more, right? So where you can see in these regions, no, obviously the magnetic field lines are very close, as you can see in these regions, right? So they are very close here, right? So the magnetic field, where they are close to each other, there the magnetic field is stronger. Okay, the first part. Second, what happened to the magnetic field when the current in the circuit is reversed? Now, this is a question which we'll understand through a figure. Okay, so as you can see in this figure, students, that initially the current is flowing. This is positive and this is negative. The current will be flowing in this direction like this. Okay, and when you will see from the top, what will be this? This will be in clockwise or anti-clockwise. This is rotating like this, and you're watching from the top. Obviously, what will happen? This is in clockwise direction. So whenever I'm talking, this is in clockwise direction, that means it is in this direction. Which pole will be this? This will be south pole, right? As you can see, the magnetic field lines are entering into this, right? Emerging here, and these are entering here, right? So from north to south. So this is north pole and this is south pole. It is clear. But they are asking us what will happen if the current in the circuit is reversed. So instead of this battery, students, okay, instead of this battery, now we don't have this battery. Instead of that, say for example, we have a battery which is here and the terminals are connected like this. Okay, so this is a circuit diagram, new circuit diagram which we have. Now this is plus and this is minus, right? So what will happen? Now the current will flow like this, right? So same way, what will happen? Instead, because initially the current was flowing like this, now the current is flowing from this terminal to that terminal. So what will happen now? This coil, when you will watch from here, will act as south pole. So this will be south and this will be north, right? Now the process will be reversed. The current direction, the lines will be emerging in this direction in this case. Okay, so they'll be starting emerging from north and it will be entering into the south. Okay, like this. So now what they are asking us, obviously, what will happen? What happens to the magnetic field lines? Obviously, the magnetic field lines will also get reversed if you are reversing the battery. If you are reversing the terminals of the battery, if you are reversing the current, the magnetic field lines will also reverse. Clear? Okay. Now, this is a case-based study question, 4 marks question. So question number 15, Ansari sir was demonstrating an experiment in his class with the setup. So this is the setup which is shown here. Okay, we have a spring here. This is a magnet, moving magnet, and this is a stationary coil and Faraday a galvanometer. No source we have, right? No current source we have, no voltage source we have. So what they are asking us in this question, what he did, he lifted the magnet. So Ansari sir, he lifted the magnet, and what happened when he released it, this magnet started oscillating, right? So inside out the coil, stationary coil, it will keep on oscillating like this. Okay, the first question which they are asking us, what is the principle which Ansari sir is trying to demonstrate? So you all know it, it's electromagnetic induction. Very good. So second part, what will be observed when the magnet starts oscillating through the coil? So when this magnet starts oscillating, what will happen? When this is oscillating, what is happening basically behind you have studied, right? When the magnet is oscillating, the magnetic field lines will also change, right? Due to that change, a current will be induced because of the induced EMF. So a current will be induced. This galvanometer will be showing us the deflection due to that induced current, right? So what is the reason behind that? Obviously, that is the change in the magnetic field. Always remember, this change word is very important, right? If there will be no change in the magnetic field, there is no change in the magnetic fields, that means there will be no EMF or the current induced in the circuit, right? C part. Consider a situation where the magnet goes in and out of the coil. State two changes which could be made to increase the deflection. So you have to tell which two changes you can make in this setup itself, in this setup only, so that to increase the deflection in the galvanometer. Okay, obviously what you can do, the two parameters which you can see here, what you can do here is that the first thing which you can do is that basically you can increase the strength. You can increase the number of coils, right? The number of coils which you have in the stationary coil, you can increase that. Also, you can increase the strength of the magnet. So according to this whole setup, these two are the things which you can change, right? So we can use a stronger magnet and the coil which has more number of turns, right? So these are how the marks was segregated in this question. For total 4 marks question, 1 mark for electromagnetic induction, 1 marks for the second part, and 2 marks for how you can do that. Okay, the or part. So either the above or this one. Don't try to attempt both the parts, okay? Is there any difference in the observation in the galvanometer? In the galvanometer when the magnet swing in and then out of the stationary coil? Justify your answer. So they are asking us, will there be any difference in the observation in the galvanometer when the magnets swing, it is coming in, and when it is going out? Yes, there will be difference, right? And you know that very well. What will happen? Say, for example, when the magnet is going inside the coil, there will be change in the magnetic field. So due to that change, what will happen? The galvanometer will show some deflection. Say, for example, let us see when it was coming in, it shows a deflection here. Okay, when it will come out, now the magnetic field lines will again change, but this time the magnetic field lines will be decreasing. So one time it's increasing, other time it's decreasing. So obviously the deflection will be on the other side. So if the deflection at one time is on the one side, that is, say for example on the left side, then on other time when it is coming out, the deflection will be on the right side. So when the magnet moves in the coil, the ammeters show a momentary deflection. So this deflection will be a small deflection for a moment, right? So say for example, it comes to a left first, then it will come to a right. So both time it will be opposite to each other. Now what they are asking us, justify your answer. They're telling us, can you justify? Yes, this is due to the change in the magnetic field, or we can say the flux associated with the coil. Flux is basically, you can understand, it's the amount of magnetic field lines which are passing through a per unit area, right? So that is the flux. So how much change is there in the magnetic field lines, that will depend how much deflection we'll get in the galvanometer. So alternatively, the flux increases when the magnet goes in and it decreases when the magnet goes out. So these are the marks segregation, how the marks will be segregated for this question. So I think if you know your concept, if you know them very well, then you will be able to attempt the questions very well. And these are the basic questions, right? If you know the basic concept, you'll be much confident to solve them. So that's it from my end. Thank you so much. Bye-bye. See you soon. Bye.